Thank you for the introduction. So I will report on joint work in progress with Kirano Grady about the moduli of quartic surfaces and what is the revisited part. So there was quite a bit of work on the moduli of quartic K-frees in the 80s, but that one was inconclusive and kind of the mantra in the 80s and even nowadays is that the degree 4 K-frees is similar to degree 2 K-frees, where we understand everything. I mean, the subject of my talk and the take-home is that actually the situation is more subtle for degree 4 K-frees, and the fact that it's so simple for degree 2 K-frees is actually some sort of accident. So, and this is work in progress. The results are not optimal at this point, but let me say. Okay, so the context of the talk is, on one hand, the problem of finding a geometric compactification for K-frees. So this is a well-known problem, and much progress was done recently, but still not solved. And the surprising thing about, and this is what we discovered working on this problem, is that this is related to the problem of birational geometry of moduli spaces. And when one says this one understands the Hassett-Kiel program for MG bar. I will introduce it later and discuss, and maybe a bit optimistically, let me announce a Hassett-Kiel Looijenga program for K-frees. So I think something like Hassett-Kiel can be done for surfaces and whatever. There is some work on this, and I'll report. So let me set up the problem and what we are discussing. So the problem is to consider the moduli of K-frees. This is moduli of degree D K-frees, and to try to compactify it in a geometrically meaningful way. So what do we know about this one? So we know that this one is isomorphic with the quotient of a 19-dimensional type 4 domain. So I think to this audience is no need to introduce the period domain for K-free. So this is a Hermitian symmetric domain of type 4, modulo an arithmetic group, and arithmetic group depends on the degree. As such, it has natural compactifications, which have to do with the arithmetic of the group gamma D and so on. So the first one is the Satake-Bailey-Borel, which is basically you just add points. Maybe you'll hear something like type 3 components, which in this situation are just points, and some modular curves. So this is the boundary, and these are the so-called type 2. As you see, this is very small. And of course, this would be very singular. But of course, on the other hand, we have that this is canonical and in some sort minimal. And if I get a paper to referee for about compactifications of K-frees or something, if it doesn't involve the Bailey-Borel, I automatically reject it, because kind of the Bailey-Borel is God-given and everything is built starting from Bailey-Borel. So in some sense, the goal is to refine in a meaningful way this Bailey-Borel. So there are the toroidal compactifications. So these are the toroidal compactifications of Mumford et al., which are may be nice might be nice. So you can arrange them to be projective, almost smooth, and so on, but depend on a choice. And finally, in between those two, I mean, generalizing both of them, are the semi-toric compactifications of Looijenga. And although they play an important role in what I'm saying today, I'll just say that they interpolate between Bailey-Borel and the toroidal compactifications. That's enough for today. But what's the issue with this natural compactification is the geometric meaning. Should I say a word about the semi-toric, or? I mean, in some sense, I mean, so some people are saying nice. So there is a result of Alexeyev, I think, that says that that's a low canonical space. So if you are happy about low canonical, then that's nice. But anyway, the point from the geometric perspective, the main point, and why you want to refine those is those are too small. So you only add one-dimensional boundary stratum, so it doesn't capture the geometry. From the perspective of the degenerations of Hodge structures and so on, the Satake-Bailey-Borel captures the graded pieces of the limit mixed Hodge structure. The toroidal compactification captured the full mixed Hodge structure with prescribed monodromies. Anyway, so the point is that you don't have geometric meaning, and I mean, kind of the goal would be to establish something like AG Voronoi is modular. This is a result of Alexeyev based on Mumford and Namikawa. So this would be kind of so you have a specific toroidal compactification that has geometric meaning, and I should announce that whatever Alexeyev announced something like this for degree 2. But this is, again, pretty by accident. So we have something geometric. For low degrees, we have GIT models. And in my notation, the GIT model would be always M bar. So for today's talk, this would be GIT for quartic surfaces, or maybe GIT for sextic curves. So you have a GIT model which always has a weak geometric meaning. So even if you don't like GIT and so on, always GIT has a weak geometric meaning in the sense that all the points in the GIT quotient are in one-to-one correspondence with polystable orbits. So this is not a modular meaning, but it has some geometric meaning. And you have a birational map to D mod gamma star. You have a good locus. So again, today M would be the good moduli. So this would be, for instance, quartics with ADE singularities. And the goal, so the main goal is to find an explicit resolution of this birational map. So the goal is to find like explicit resolution of this birational map. The point is, so why? So the point is that this has structure. So this is a very nice space with a lot of structure coming from arithmetic, and this has geometric meaning, and in some sense M tilde reconcile both of these ones. And actually the motivation of our work, so motivation of why we look at this one and why we, is the moduli of EPW sextics. So these are hypercalars of dimension 4 of degree, if you want to. And this is a lot of work of Kirano-Grady, and we started working on the moduli of EPW sextics, hoping to prove something similar to what I did for cubic fourfolds. We failed, and we realized that the failure is due to the degree 4K free surfaces. And then, in fact, we realized that we cannot really do even the degree 4K free surfaces, and the failure is due to hyperelliptic K-frees, and we understand those, and now we are in the process of going back. So anyway, so this is the goal, and just to keep in mind, so the degree 2 K-frees, and surprisingly also the cubic fourfolds. So in some sense, the quartic K-frees, if I'm not, okay, essentially those, the moduli of quartic K-frees is the normalization of the discriminant divisor for EPW sextics. So the point is that in all these kind of moduli problems, you see one lower dimension embedded into a smaller dimension. So the point is that for degree 2 and cubic fourfolds, we have a good understanding, and let me just give you the 2 minutes presentation of the degree 2. So you have the GIT, you have the map to D mod gamma star, and it turns out that all you need to do to resolve is, so this is omega, this is the orbit of the triple conic. This is a polystable point, so you can interpret it as a point in the GIT quotient. You blow up this thing. This is the blow up, the Kir-1 blow up, so it's canonical from a GIT perspective. And once you do this one, you resolve the map. This would map to unigonal K-frees, the exceptional divisor, which is the same thing as elliptic K-frees with a section. And finally, this one is also nothing else but a semi-toric compactification. So in the degree 2 case, you just blow one point on the GIT side, and you recover one of the semi-toric compactifications. It's as simple as possible. For cubic fourfolds, is slightly more complicated, but of the same nature. And kind of the warning is that degree 4 is different. Okay, so let's see what's the difference and how we suggest. So let me discuss in general GIT versus Bailey-Borel for K-free types. And this is mostly work of Looijenga. So let's start with a couple of basic observations. So the first observation is that both GIT and the Bailey-Borel are projective varieties with tautological polarization. And tautological, of course, has to be put in between brackets. So in some sense, they should coincide. They should essentially coincide. So let me explain a bit about this one. So we have the let me just recall. So D mod gamma star, this is proj of the ring of automorphic forms. So I will denote the automorphic line bundle L. So this is like that. And M bar is proj of the ring so this is the line bundle on some Hilbert scheme, and you are taking G invariant sections. These are of different nature, but of course these line bundles descend on the moduli space, and essentially they coincide. So that's the basic idea. So what is the general comparison? So general comparison of projective varieties. This is kind of the key point. So if we have X proj of the ring of section of some ample line bundle, and similarly Y is proj of the ring of section of some other line bundle, typically in this kind of situation we have U embedded in both, some common open subset, and we make two assumptions. So we assume that the codimension in X and Y of U is of boundary of U is greater than 2. So isomorphism in codimension 1. And we assume that we can prove that Lx restricted to U can be identified to Lx restricted to Y. Then it turns out, then it's trivial that X is isomorphic to Y because sections extend in codimension 2. So this is kind of the general comparison, and this is what we want to apply. And on the GIT side, the codimension larger than 2 is always satisfied. It's not, you can contradict me, but basically on the GIT side, you define the good locus in a way that the codimension 2 is satisfied. The tautological line bundle, and we'll come back to that, guarantees in some sense that this thing is true. So we have to worry about the codimension larger than 2 on the other side. And the second observation, this is... No. You'll see. Okay, let me say it. So because I'm taking M, my M is like quartics with AD singularities. So it turns out that typically the image of period maps to type 4 or complex balls is complement of a hyperplane arrangement. So typically, what's going on is that I have M. Of course, you have to be in a situation when global Torelli holds, but typically in these situations we know. So typically, M is an open embedding into D mod gamma, I don't know if you want star, with image of P is D minus H mod gamma. For example, for degree 4K freeze, so M is quartics surfaces with ADE, then the image of P is D minus H unigonal union H hyperelliptic mod gamma. So these are unigonal, these are hyperelliptic. So these are elliptic A-frees. These are double covers of the quadric. And this is simply a consequence of Meyer's theorem on linear system on K-frees. And kind of the goal of Kiran was to study the EPW66 and the image of the period map for those in order to understand kind of an analog of Meyer's theorem. So Kiran wanted to go in the opposite direction. That's why kind of the example of EPW66 is more interesting. So why is so? So what's going on here? And I should hurry up. So the reason, the moral reason for this one is a theorem of Tsarus, which roughly says, so don't quote me on this one, so but essentially says for K-frees, and maybe more generally K-free type, the maximal Mumford-Tate subdomains of D are hyperplanes. So which means acquire an additional Hodge class. Maximal with respect to the inclusion. So you have I mean, and this is kind of what's different from, I mean, this is special for type 4 domains and these kind of Ball quotients. For any other Hermitian symmetric domain, actually is much more complicated, in particular for abelian varieties. So any kind of degeneration that you detect Hodge theoretically, it will actually land into one of these hyperplane arrangements. So the hyperplanes, let me say it just in the Noether-Lefschetz loci. I mean, actually, it's a bit of cheating here, but let's, for K-frees is actually true because you can also have the endomorphism. This is the theorem of Tsarus. So the theorem of Tsarus, it says the only relevant Hodge tensor for K-frees are weight 1 and weight 2. So no, you don't have. And for K-frees, if you have a weight 2 Hodge tensors just because the dimension is 19 and whatever it splits and so on, it will actually land into a hyperplane. Yeah, but for K-frees, actually, it forces a Hodge tensor also. Yeah, a Hodge tensor of weight 1. So if you have an endomorphism, then it will split into eigenspaces, the period domain, but the domain is 19-dimensional, so you cannot split 19, so you have to split something like 18-dimensional. I mean, so you can have a Ball quotient of dimension 9, but this will sit into an 18-dimensional, this will sit in a 19-dimensional, so you would have a Hodge tensor. So, one, so a Hodge tensor, a Hodge class, so a 1-1 class. So for K-frees, it's true that if you have an endomorphism, then you get, just because it's 9. No, so that's what I'm saying. So in other cases, it might be true. But anyway, Tsarus says, I mean, if you want to be correct, weight 1 and weight 2 Hodge tensors, but for K-frees, you can reduce. Anyway, so it says that if you have a degenerations of, that you detect it in any Hodge sense, then it will land into one of these hyperplanes. So the problem is that, of course, I mean, we need codimension 2, and this is kind of what Edward did. So the point is that this divisor can be contracted. So what he did is, so for H, a gamma invariant arrangement, he constructed a compactification D mod gamma H. So this is a modification of Bailey-Borel such that codimension is larger than 2. And we need an assumption. The assumption is that H19 is empty. So let me denote by HK. This is a kth codimension linear stratum for the hyperplane arrangement. So no intersection in dimension 0. And let me kind of say a few more words how that works. And then, of course, basically, once you have this one, you get that this M bar is isomorphic with this modification. And this is true for degree 2 and cubic 4/4. But this fails for degree 4. And I will explain why. So what is the construction of this D mod gamma H? Let me just briefly recall. So you have D mod gamma star. You need to do a small semi-toric resolution. So this is a small map. So actually, in the cases that we are looking, you have something of dimension 1. It will become of dimension 2 upstairs. And why you need to do this one? You need this one to make H mod gamma bar Q Cartier. So basically, this is something dictated by the minimal model program. In order to do birational geometry, you need to do some sort of Q factorialization. And this is the first step. And you can do it and he analyze what's happening at the boundary and why. I mean, of course, this H mod gamma is Q Cartier in the interior, so the only issue is at the boundary. Then you do a wonderful blow up. So this is a blow up of the hyperplane arrangement such that you become two normal crossings, and then you can contract in the opposite direction. So the hyperplane arrangement H would give you a point. Codimension 2 strata will give you a curve, and so on. So if you do this thing, the codimension 19, so the things of maximal intersection will give you a divisor. Because you see, so what's happening in this kind of situation? You have a hyperplane arrangement, and when you blow it up, you do that, and then you contract it in the opposite direction. So you contract this thing, you'll get something like this. So it's a flip, and this is well. And you see, so kind of the key assumption here is that you don't have intersections in codimension 19, because those, by this procedure, will give you divisors and you gain nothing. Okay, so let me explain now, I mean, kind of the paradox why, for instance, even cubic 4/4 seems simpler than degree 4. And this is kind of like just an arithmetic explanation. So let's see what's going on. So arithmetic of degree 2 and 4 K3s. So we always have this hyperplane arrangement, the nodal, the unigonal, and the hyperelliptic. So these are whatever. So this corresponds, you have the polarization, and you acquire a node, you acquire a -2 class. The unigonal is you have the polarization, and you acquire a -2 class, and then this will give you the elliptic K-free. So these are, if you want, K-free surfaces marked by these kind of things, and the hyperelliptic, these are K-frees that are double cover over a surface, and these have generically this polarization. These neurons are very lattice. Okay, so these are these things. For degree 2, the only relevant one are the nodal and the unigonal, and for the degree 4, the nodal, the unigonal, and the hyperelliptic. Of course, the nodal, this is the ADE, we don't really care, but we look at this kind of hyperplane arrangements, and the question is, what is the linear stratification induced by them? I mean, the elliptic, I mean, unigonal, it means elliptic K-free with a section. So, I mean, so unigonal, I mean, it's kind of a shorthand for that. And hyperelliptic, it means hyperelliptic 2 to 1 over a rational surface. So the linear system is not ample. And this is basically Meyer's theorem. So it tells you, I mean, Meyer's theorem tells you what the behavior of the linear system. And these are the three cases kind of you have to care about this one. And I mean, so the nodal, we ignore it because this is kind of included in both moduli spaces. Yeah, it's just a point. It's just a point, so you need to blow up that point and that. So, but you see, so in general, kind of the process and kind of the point that you have to understand is how these hyperplane arrangements meet together, because that's kind of his recipe. And I'm saying, so the point is that basically in degree 2 is no self-intersection. So this is simple. I mean, if it's no self-intersection, basically you don't have this step, so you just do this one and then contract. But on the other hand, in degree 4, you have actually the hyperelliptic intersects up to codimension 19. So this is why you have failure. So the conclusion of this one is that you need to modify the GIT so that the hyperelliptic one is included, is in the good locus. So we want to do, I mean, kind of our plan is to do GIT for twice embedding quartics, and then probably it will work out. Yeah. I wrote it here. So HK is a K, codimension K linear stratum associated to the hyperplane arrangement. And I'm explaining now, so this one, okay, so this is a fact, and I mean, you can see it in many ways. But there is like a trick that I learned from Kondo, so this is like Borcher's trick. Borcher's trick. And this is, let me just say it parenthetically. So it turns out that the best way to understand the arithmetic of K-free surfaces, and Klaus and with his collaborators, Grisenko and Sankaran, got a lot of mileage of that, is to actually consider the K-free lattice. So we are considering lambda d, which is the polarized K-free lattice, so minus d plus 2 copies of E8 plus U square, and to embed it into the Borcher's lattice. So this is 3 copies of E8 plus U square. So instead of embedding it into the K-free lattice, you embedded it into the Borcher's lattice, and you get a lot of mileage out of this. For instance, you have the Borcher's automatic So this means that you embed the moduli space of K-frees in a 26-dimensional moduli space. Here you have the Borcher's form, automorphic form. You pull it back to the domain, and you get a lot of mileage out of this. So so this exists, and there exists a primitive embedding. There exists a primitive embedding here, and I care about degree 2. So for degree 2, the orthogonal complement of lambda d of lambda 2 turns out to be E7 in this embedding, and for degree 4, it turns out to be D7. So in degree 2 and 4, I think the embedding is unique, and whatever, you take this primitive embedding, and the orthogonal complement would be E7 and D7. So they look pretty similar. And I will put it in the following form. So I'll put it in the following form. So this is a lemma. So there exists phi mapping the K-free lattice. So this is a K-free lattice to the Borcher's lattice 226, such that phi inverse of the polarization. So here you have the, wait a minute, the other way around. Surjection. This is a surjection. So there exist surjections from the Borcher's lattice to the K-free lattice, such that if I'm taking the polarization here, this would be E7 and D7 in degree 2, degree 4, and such that phi restricted to, let's call this one R, phi restricted to R perp is an isometry. So okay, so this is a bit confusing when you see it first time, because you see this is signature 319, this is signature 226. But when you restrict to the orthogonal complement, they become signature. If you take the orthogonal complement in both situations, they will become signature 219 in both situations, and it can be an isometry. And I mean, so this one, I learned it, this formulation, I learned it from the paper of Thomas and Addington for about cubic fourfolds. This is supposed to be some sort of K group, and this is supposed to be some sort of homology. And there is some sort of shift when you go from this one to that one. And I mean, so this is the monster conjecture of, monster conjecture of Alcock, and maybe I think also Kontsevich has something about this one. This is supposed to come some sort of moduli space of some sort of hyperkellers with Betty number, I don't know, 28 or something, 29. So, but of course this is, I mean, so it behaves, this kind of thing behaves, and this is kind of, this behaves as being a moduli space and whatever. But anyway, the point is that this lemma and stuff like that is purely arithmetic. And what's the corollary of that one? Of that lemma. So corollary is that the hyperplane arrangement Hn, H, and Hu correspond to acquiring an additional -2 class in Borcher's marking. So you see, so here in the K3 marking, you have something like 4, 0, 0, minus 2. If you take phi inverse of that, it turns out this would correspond to D7 plus A1. And similarly, if you take the 0, 1, 0, 0, this would correspond to D7 acquiring an additional class and becoming E8. And finally, 0, 2, 2, 0 corresponds to acquiring D7, D7 going into D8. So you acquire an additional Hodge class here, which might be complicated, and you have issues of primitivity and stuff like that. But if you pull it back by Borcher's marking, it has a uniform description. You simply acquire an additional -2 class. And now it's easy to see the intersections of hyperplanes. So strata in HK would simply correspond to acquire K -2 classes. So now it's easy to see that H unigonal does not self-intersect, because you go from D7 to E8 and you cannot extend this one. But on the other hand, if you have hyperelliptic, this self-intersects up to codimension 19. Because you go D7, D8, you can acquire an additional class and so on. And for cubic, I mean, the lucky thing about cubic fourfolds is that you start with E6. So the same lemma applies, but you start with E6. So if you acquire an additional class for E6, you can only go to E6 plus A1, E7. And then the next level would be E8, and then you stop. So this is kind of the arithmetic, a simple explanation. Why is this different? So they are different arithmetically. OK, so the upshot of this one is that we need to do something different. So let's go to results for quartics. So, of course, this was Shah and Durabe in the 80s, and we basically revised this one, and I can speak for a couple of hours about the revised GIT. This is ourself. But let me just give the flavor of this one. So basically, you have M bar, and here you have two special points, omega and zeta. So omega corresponds to the tangent developable to twisted cubic, and this corresponds to double quadric. So you have the twisted cubic, and you take the tangent variety to that. So you are taking the tangents to the twisted cubic. That turns out to be a quartic, and these are GIT semi-stable points. And you blow up, as before, you blow up those points, and you get two exceptional divisors, EW and EZ. W maps to H unigonal mod gamma, and basically that's the end of it. And E zeta maps to the generic point of the hyperelliptic. But then but here you have Z, which is a type 4 locus, which is basically the indeterminacy locus. And this indeterminacy locus corresponds to double covers of quadricon. But this has to be some sort of flips involved over this locus. So this is dimension 10, this is relatively small, and this is codimension 2. So basically the picture is you have this M tilde minus Z is isomorphic with D minus this kind of H2, hyperelliptic 2, mod gamma, and some sort of semi-toric compactification, plus flips over Z. So basically what's happening, and I can describe more, but let me just give the basic thing. So Z is stratified, and kind of the deepest stratum from here will correspond to this kind of H2. But inside H2 you would have H3, which would correspond to some sort of curve, and so on. So it's the usual flip that involves hyperplanes arrangement. So you have the top dimensional thing is contracted to a point, the codimension 2 thing will become a curve, and so on. But kind of the problem is that this is codimension 2, and this is codimension whatever 10. So at some point something happens. So this is, I mean, if it were a perfect flipping, you'll have also this one of codimension 2. And then whatever, we took a closer look, and let's see what we discover. So, and let me discuss about the Hassett-Kiel problem. So actually, if you look here, so basically here the question that is essentially is to compare GIT for double covers of quadric surface versus the Bailey-Borel D mod gamma. This is 18 dimensional. This is the moduli of of hyperelliptic K-freeze. So what I'm saying is that everything that's happening, all these kind of flips and stuff like that, is happening over this locus. This is codimension 1 in the blown up stuff on the Bailey-Borel, on the GIT side, and this is codimension 1. And I mean, once you understand that, so let's see what did we do here. So let me recall what is the Hassett-Kiel and what has to do with things here. So the Hassett-Kiel is starting by looking at MG as a low canonical model. So this is proj of the ring of section of K plus delta. So this is the low canonical model. For G large, No, so I'm looking at double curve. So I'm looking at double covers of the quadricon. So these are hyperelliptic. Yeah. Yeah, but that one would be a mess because it will be embedded badly. So, but on this side you have a type 4 domain, and you have the comparison with the GIT, which are four curves on P1 cross P1. And kind of the point is, okay, let me just try to explain. So this one we understand. So okay. I will run out of time to explain exactly how we understand. This is okay. This we actually understand. We understand, and this is related. This is okay. Maybe I'll say something. So that one we understand, and then is a problem. But that one, trying to understand that one, give us into this kind of problem. So let's back up for curves a bit. So for curves, you know that mg bar is proj of k of the canonical on mg bar plus the discriminant divisor, the nodal divisor parameterizing nodal things. You know that for G large, mg is of general type. So by general things, you say that I have a canonical model, which is just proj of R k, so without delta. And the question is, what is this one? And Hassett-Keel, what they did was to say, oh, well, I can interpolate with mg alpha, which is proj of R k plus alpha delta. Of course, when alpha equals 1, I get that one. When alpha equals 0, I get the other one. And the point is that as alpha varies, so for alpha 1, we understand everything. So alpha equals 1 is okay. And then as alpha goes to 0, we get various birational models, which turns out to have geometric meaning. So the first relevant thing is as you go from mg bar to mg bar 9/11, where you get the moduli of pseudo-stable curves, which means you allow cusps okay, but not elliptic tails. And as you go deeper and deeper, as you run the program and you decrease alpha, at the next step you'll allow tuck nodes and will remove elliptic bridges and so on and so forth. And what's the point here? So in some sense, this is what we are doing. So in some sense, morally, we do the same for K-frees. Because basically, it turns out that in some sense, the Bailey-Borel parameterizes in a weak sense, SLC degenerations of K-frees. I mean, this is a bit of a lie, but you can take it in this one. And the GIT parameterizes K-free degeneration with worse than SLC. So in the quartic situation, for quartics you get E12, E13, and so on. And for non-experts, these are the Dolgachev singularities. These are the simplest non-SLC, non-low canonical singularities. These are, in a good sense, analog of cusps, in surfaces. So morally speaking, you are doing the same here, and again, kind of like in this kind of story, you are doing the same here. But actually, it's more than that. So it's actually not only kind of morally, because what's happening is that in the Hassett-Kill program, most of the mg alpha are obtained by GIT. So let me recall that Mumford and Gieseker show that if you take a curve, you are taking the mu canonical embedding into Pn, and you are taking the Chow quotient, Chow mu mod SL n plus 1. This is isomorphic with mg bar for mu larger equal to 5. For mu less than 5, and maybe using Hilbert instead of Chow, you get the various mg alpha. And what is the point? The point is that all these spaces are tautologically polarized by some sort of linear combination, of lambda and delta, or maybe, if you want, k and delta. And this is a famous computation. This is a famous computation of Mumford and Knudsen. So remember what I said, that kind of the GIT and the Bailey-Borel and stuff like that are tautologically polarized. But I mean, the tautological polarization is, I mean, the tautological classes on the moduli of K-frees are things like lambda and delta and various combinations of those. And the fact that you get various models comes from the fact that you have various linear combinations of those. And exactly the same situation is true for K-frees. And let me just briefly say something about that one. So same for K-frees. So for instance, first of all, the D mod gamma star, it turns out this is just proj of the lambda class. So you can view this one like that. You have a formula analog, so remember for mg bar, you have a formula roughly, I mean, this is k is 13 lambda minus 2 delta. We have the same formula for K-frees. And let me say something. So for K-frees, k is 19 lambda minus 1 delta. And then the question is, basically then the question, and roughly speaking, the polarity. And this delta here, this is the ramification divisor for D mapping to D mod gamma. This is, in most of the cases, coming from the nodal plus unigonal plus hyperelliptic mod gamma. And then the question is, this is what we are doing now. This is compute the Chow and Hilbert scheme polarizations for moduli of K-frees. So basically, you are taking a K-free, you are embedding it by a big, I mean, you want to embed it by small, but anyway, so you are embedding it by lambda mu, and then you get the Chow mu mod SLN. And we know how to compute that one. I mean, is not yet prime time. But anyway, so the point is, for instance, let me put close with a theorem. This is for 4 curves, we prove that Shah1 modulo SL for this is isomorphic D gamma star. And we also know how this is different from GIT for 4 curves on P1 cross P1. And kind of the hope, so I don't know if it's, I mean, what we hope to prove is that basically Chow2 for degree 4K freeze, this is roughly the same as D1 gamma star. That's more or less, depending on which day of the week we are looking at it, that's okay, let me stop here.